Okay, so as Debbie mentioned, and thank you, Debbie, for that gracious introduction. Really appreciate that. It's been a pleasure to work with you and eSig over the past many years, and we've come a long way, I think, in understanding the integration of inverter-based resources and variable energy resources. I want to talk for the first 40 minutes or so about some of the basics and build from there. So Nick and I will take you through a journey about some of the stability aspects, as Debbie said, and really want to start off by talking about some of the differences of where we've been and where we're going as the resource mix changes. And the first part of that discussion, the first very important part, is to recognize some of the differences in conventional synchronous resources relative to inverter-based resources like wind and solar. So with the conventional synchronous resources, these resources are synchronized to the grid with a synchronous machine. They're directly coupled, and the amount of the stability and the power that's being given to the grid to serve the demand and all the behavior is directly coupled based on the machine and the machine design, and it's more based on the physical attributes of that machine and how it interacts with the grid. And obviously there are controls like excitation to control voltage. We'll go over what that means, and other aspects of the synchronous machine like a governor to control speed and maintain frequency that is very important to the overall capability. But the inverter-based resources are just that. They are interfaced with power electronics. And those power electronics really dominate the overall behavior and performance of the inverter-based resources, the wind, the solar, also batteries. There's also other grid support devices. It's called flexible alternating current transmission support devices that are inverter-based as well. But all of those devices have a characteristic that's dominated by their controls. So let's get into some of what that really means. So want to really pull on some very key points that we really want to deliver throughout the entire rest of the talk here that both Nick and Julia and I will be talking about. So we're going to touch on the importance of frequency management, touch on the importance of voltage management, but the notion of grid strength and how strong or how relatively dominant are inverter-based resources in any particular area compared to synchronous resources. That is more of an urgent issue than the frequency problem is. And the coordination and interoperability of all resources to be able to manage that is critically important. So we'll get a lot more in depth in what that means. Export stability, sharing the capability across regions is more of an urgent issue than low inertia as well. And performance of inverter-based resources is critical to be able to port the capabilities of the advanced controls that we've invested in over the past couple of decades, and being able to manage that and port those capabilities onto the grid as necessary. It's not just about building the capability in the equipment, but making sure it's utilized with codes and standards and interconnection requirements and market mechanisms to be able to couple those onto the grid. We'll talk a lot more about that later on. So no fear, the sky is not falling. We are really in a point now where technology fundamentally is not the limitation from any resource, but rather how all resources work together and how those capabilities are given and how they're enabled on the grid. So we're going to talk a lot about enabling those technologies and the interoperability between everything. Synchronous generators and inverter-based resources are different, but that's not bad. It goes back to how to make them all work together. So with that, let's point out some very basic things. Modern grids, get rid of my window here so I can see the entire slide. Great. Modern grids have no hard limit in terms of the integration capability of any resource. It's more a matter of how those resources work together, a matter of integration cost, but moderate annual averages that you see, in this case, we're showing Xcel Energy, 5 years ago, where on average over the year, we had 25% annual energy being served from wind and solar. But that 25% averaged over the year really equates to much higher instantaneous time periods, much higher number of hours or instantaneous penetration, I should say, being served by wind and sun during those peak periods when it's windy and when it's sunny. So 25% annual energy 5 years ago in Xcel Energy turned out to be over 70% instantaneous penetration for a couple hours during the year. And the question is, how do we make sure we can maintain stability under all of those operating scenarios when we have higher penetrations, even though they are only a few hours a year? So, okay, that's what happened with 25% annual energy. What happens with 55% annual energy in 2025 when Xcel increases their penetration and can have more energy being served? What does that look like in the footprint, and how does Xcel cooperate with its neighbors in order to be able to achieve that penetration, especially instantaneous penetration that approaches 100%? Oops. So right now today, in fact, there's recently a record in SPP that occurred in May this year, where 85 or over 87% of the load of the demand was served by inverter-based resources, by wind and solar. And at that time, everything was just fine. It required balancing. It required all the things that we're going to talk about. It required stability, but everything was just fine in that period of time. And we are now approaching today very much instantaneous penetrations that are trying to get to 100%. And I emphasize trying because if we were not otherwise controlling or curtailing wind and sun in certain cases, then we could really today achieve very close to 100% penetration in islanded areas like Ireland, for example, close to 100%, over 80% anyway. Texas, Julia will talk about what's going on in Texas. There's new records that are being broken in Texas as well. So the penetrations keep climbing and everything is okay, but it's a matter of coordination of control and making sure we support the grid with all the resources as needed. So it's not only about what happens during normal operation, right? But we live in a world that has disturbances. Murphy's Law says that we're going to get an outage somewhere, sometime. We have storms that come through. We have outages that occur in the system. And it's not only about what happens during the normal operation, but those outages create very large electrical islands, even in the bigger interconnections, that we have to maintain stability in those states as well. So you see here some time ago, there was a penetration where 80% of the load in the northern part of MISO was served for a couple hours in 2016, in November of 2016 at 4 a.m. when the load was light. And at that particular point, those were situations where we needed to make sure that we can balance the system adequately and keep the system stable with that high amount of energy being served from inverter-based resources. So both in regular, normal operation, undisturbed, and during disturbances, that's what we need to worry about in terms of maintaining stability and control. So how do we get from where we are now to perhaps looking at a few hours during the year to really shifting to more mainstream and including all of the needs to keep the system stable, reliable, and interoperable for more hours during the year under more normal and disturbed operating conditions? And it really requires a paradigm shift in many regards. This is a slide that we have, that many of you have seen before from Migrate some years ago. And looking at where we are today on the blue line, pushing the limits of the capabilities of equipment, pushing the capabilities of inverter-based resources to have a little bit more capability to maintain stability, to support frequency and voltage in different ways, to push a little bit more power over the network is certainly something that we've gotten good at over the past many years as we're growing the penetration. But it's going to take a paradigm shift in terms of technology deployment, implementation, and how we deploy and plan for those situations where we have more regular capability to serve the load more often, and when we don't have as much synchronous generation online at that time, getting more getting more power to flow from inverter-based resources and do it stably really is going to require a paradigm shift in terms of controls, coordination, protection, modeling, planning, everything we're going to talk about going forward. So where we have been so far, the vast majority of existing technology today is not a problem at all. We can regulate voltage, we can support frequency, we can do it stably and reliably without a problem. And in some cases, we've learned how to push the limits of those existing controls where necessary, especially in some of the islanded systems like Texas, like Australia, like Ireland, like Hawaii, where we have more hours fed with higher penetrations of inverter-based resources, where things start to get a little bit more difficult to maintain the stability in the network. But still, those capabilities are there. What we're really focused on today is looking at new technology capability, hybridizing wind and solar and energy storage, as well as looking at capabilities of new control topology, like grid forming inverters that actually fundamentally change the capability to make these inverter-based resources look and act more like synchronous machines on the grid. It doesn't have to be 100% of those resources having grid forming capability. We're still figuring out all of what is needed to shift, but that capability is certainly there, and we have demonstrated projects that are online right now that support voltage and frequency in very difficult operating conditions, weaker and weaker grids, supporting system inertia, supporting system frequency recovery in the ways that are needed. So we are still trying to figure out this transition. We're in the very early stages of starting it. Models and capabilities and grid codes as well are just evolving to deploy it. But let's talk about some of the details. So,
Jason, you're going to need to speed up because we're about halfway through.
Okay. So stability has multiple facets in terms of frequency support, system stability, and transient stability that we're all going to talk about. So we'll talk about frequency control, small signal stability analysis, transient stability analysis. So in terms of frequency, how do we manage frequency? First of all, when there's a system event, when the generator trips offline, frequency is basically machine speed, that if we lose a generator online, machine speed drops. The rate of change of that drop is based on what inertia is online at the time. And then eventually it gets down to a point where we need to arrest that initial drop and recover that electrical speed and maintain a balance between load and generation. So there are many ways to do that. The initial decline, as you have more inverter-based resources without capability to support frequency and voltage, yes, the decline might get a little bit steeper. But today, in the interconnected systems, that's not a problem. There's certainly capability from inverter-based resources, from fast frequency response, primary frequency response, to provide energy to rebalance the system and bring the frequency back and recover after an event is there. So it's more about how to coordinate this and make the system rebound, and eventually, in longer time periods, automatic generation control in tens of seconds can bring the system back up, rebalance the system, and eventually the tertiary control, where the redispatch of all the generation to make up for the loss of that individual unit or plant that we lost, will redispatch the system and bring the frequency back to where it's needed. So it's not a problem as long as the deployable capability is online and available from all resources. So Julie's going to talk a lot more about this a little bit later, but we have the interconnected systems in the East and the West, and also separately in Texas. Frequency control is more difficult in islanded systems. It's not really an issue right now in the interconnected systems. We have a lot of support from the current capabilities of the generation in the interconnections that we have right now. Julie will talk more about that a little bit later. But in the Eastern interconnection, for example, we looked at this years ago, and Nick really did a lot of analysis on this back in 2012, where when we have a design basis event, we lose the frequency, we lose a large unit like a unit in Rockport up in the Northeast, and the frequency declines, but it doesn't decline all that much. You notice that it doesn't recover as well. That the recovery is something that it's a coordination between the slower coordination and the control. But eventually we were able to replicate that capability in our models and show in our models that we can actually look at the capability today of that frequency performance. But then we take that model and look at higher penetrations of wind and solar with the capability to control frequency and arrest the decline of the frequency if we lose a large generator. And fundamentally, it's not an issue. First of all, in the East, we only have a very shallow rate of change of frequency. It's very small. For that very large event, it only changes by 100 millihertz per second. And the recovery with all the inverter-based resources having all the capabilities to provide fast and primary frequency response really shows that you can recover quite well, even relative to today's capability. So it's not an issue if you deploy all of the controls and the features in the wind and the solar plants to support frequency today. Wind and solar do have the capability to provide fast and primary frequency response. And those capabilities we can see here in another study we had done together with the Department of Energy and NREL to show that the fast frequency and primary frequency response enabled out of wind and solar generation can actually support the system better than having the synchronous assets alone, as long as they're coordinated and you have the capability to arrest the decline with the fast frequency response and recover in a controlled fashion with primary frequency response that you see here on the right. So again, not a problem as long as they're deployed on the grid. So just quickly getting through this because we need to get through reactive power and others as well. Look, it's not an issue right now where frequency response is declining and it's not able to be recovered from inverter-based resources. We have the technology capability. They just need to be deployed on the grid to be able to respond in a way that is conducive to bringing the frequency back. So neither inertia or frequency response are immediate concerns. We need to pay attention, but adaptation of those controls has been slow because most of the time it's not an issue yet. We need to make sure we deploy those capabilities going forward.
Hey, Jason, I'm sorry, I made a mistake. You have until 2:50.
Okay, great. Sorry, I was going a little bit quick through that. So we're good. I'll slow down a little bit. We'll take a tour on the reactive power. I think we're in good shape. Thank you, Debbie. Okay, so that was frequency control. I went probably a little bit fast through that, and we can talk a little bit more, and if there's questions and need for clarification a little bit later on. For real and reactive power, let's talk a little bit more about voltage support and stability needs as there's more inverter-based resources coming online. So this notion of reactive power may be a little bit more obtuse for many folks, but think of it this way, that in order to have real power being transferred across the network, you need to have a certain amount of support to keep the voltage healthy in order to deliver that power across the network. And that fundamentally is the role of reactive power. The reactive power is like the head, the foam on the beer mug. And this is what all college students learn and in electrical power engineering 101. This is in terms that everyone can relate to. The beer does the work. The beer is the megawatts, and the reactive power is the head. It takes up the space, and everything together will ultimately support the needs and fill up the mug in order to ultimately maintain stability in the grid is where we're going with this. So the relationship of reactive power and voltage, let's talk about that. Think of the grid as a tank, and that tank has flows of reactive power that are provided by certain sources. So generators certainly provide that reactive power capability. It's controllable. It's injected into the grid to support the voltage. There are other sources like lightly loaded overhead lines, cable circuits, capacitive compensation in the grid, and flows of reactive power from other areas to the grid that you're talking about or looking at. So addition of reactive power from all those sources fills the tank. And when the tank fills up, the voltage generally increases if the flows out of the tank are constant. The flows out of the tank reduce the amount of reactive power in the grid, and therefore, if the flows out are greater than the flows in, the voltage decreases. So this balance of reactive power in versus out dictates the system voltage. And this is what grid operators are trying to maintain over all time periods. In the longer term, balancing out reactive power from generation to load, and especially during system disturbances, making sure that that balance is maintained. We're going to get a lot more in depth later on about how to maintain the voltage under high system stress and during system disturbances. Nick will talk about stability, transient stability, and weak systems. But remember this relationship of the more reactive power you have into the grid, voltage goes up, and then the more coming out of the grid relative to the balance, the voltage goes down, okay? And the other aspect that we want to really pull on is the challenges with voltage control are very localized. VARs do not travel well. It's voltage control and local stability of voltage regulation happens at a plant-to-plant basis, an inverter basis, and trying to maintain voltage is very localized with the balance and stability of every resource on the system. So there's a lot of detailed design and effort that goes into maintaining the stability of each inverter-based resource or each resource online to make sure it can manage its reactive power well enough and balance that without being too fast or providing too much or too little. And if any of those things happen, you can slip away and the voltage can go into place and ultimately can collapse, or you can trip parts of the grid offline. So maintaining that voltage balanced stably and reliably is a very key aspect. And again, location, location, location. Making sure that we look at all the integration of individual resources, individual plants at that particular operating point is very critical. And there's a lot of engineering that goes into an application work that goes into understanding if we have voltage control and stability issues at a plant-to-plant basis. Modeling, particularly of each individual inverter-based resource, becomes more critical. Modeling of an area to keep that stable is also very critical. But the biggest issue is knowing what type of model you have to use and what are some of the risks of having the system go unstable. Nick will talk more about that later in terms of when the voltage collapses or when we have to worry about system stability. Let's talk about steady state voltage regulation. Wind and solar PV right now have the same capability to regulate plant level interconnection voltage like any other resource. This is a plot from 15 years ago when one of the first wind plants that we integrated at GE had a plant level control that very tightly controlled the voltage at the plant interconnection point into the grid. And it actually, this plant regulated the voltage 45 miles away from the plant into the grid, even though we had a lot of fluctuation of power output into the grid. So when the power fluctuates, you tend to have fluctuations of voltage as well, because you're trying to maintain balance, right? Of losses of real power capability into the grid, but also that reactive power capability is tied to the real power balancing and the real power fluctuation. So, but fundamentally, it's not a concern. We have closed loop plant level voltage control on the system today, and it works just fine out of all inverter-based resources. The other question is, well, wind and solar can only provide voltage support when they're online, right? Well, no, that's not true either. Wind and solar capability have right now the capability to support voltage even when it's not injecting real power, even when it's not providing megawatts into the grid. The converters, the inverters can remain online and provide a source of reactive power to continue to maintain the voltage. So that's important for keeping the system stable at all periods, and you can count on these resources to provide voltage support anytime, as long as this feature is enabled and capable. So it's a matter of deploying that capability, either requiring it or incentivizing it or putting it in place to make sure that you can have that capability there. But it's not a limitation of the technology. So some key points on voltage control. Again, not a problem as long as you have the capability deployed. Closed loop voltage control is available. The key is keeping the voltage healthy where it's critical, where the power is generated, where the power is consumed, everywhere in between, keeping it healthy, keeping that balance, and making sure that you're doing it stably. And that's, Nick is going to talk a lot more about that capability to keep things stable as you have more inverter-based resources where the grids are becoming weaker. So we'll talk more about that later. Let's wrap up my session with fault ride-through and grid codes. I think we have about 10 minutes left. So what I just talked about primarily with frequency support and voltage control is done more balancing in steady state when the system is intact. Yes, for frequency response, we are worried about losing a part of the system or the largest generator on the grid, and to recover the frequency from that operating condition. But what also is another concern, but certainly has capability from inverter-based resources to support is what happens during electrical disturbances, electrical faults in the grid. Let's say you have a storm that comes through, and that storm causes two phases of a transmission line to touch one another, or causes a transmission line to break and fall to ground. That causes an electrical fault. Those faults are normally detected very quickly and cleared very quickly. But during that event, we want to make sure that when those electrical faults happen, that no other generation outside of where you have that local disturbance is tripped offline. We want to make sure that all other generation remains online, undisturbed, and supports the grid. So today, it's very common in all areas to have requirements during electrical disturbances to have generation remain online, ride through, and not trip. And that actually started from inverter-based resources more than 2 decades ago, where grids in Germany, grids in Ireland required fault ride-through capability. And the inverter-based resources early on did have a problem with the very initial non-inverter-based resource type wind generation decades ago. But we've come so far since then. Today, modern wind turbines and fundamentally all inverter-based resources that are integrated online today have better capability to withstand faults than even a lot of synchronous technology. And that is because of the capability and stability of the control and all of the advanced engineering that we put into the inverter-based resources to remain online and stable for larger and longer disturbances. So fundamentally, these requirements have happened over time. We have standards like IEEE 1547 that require it, and new standards that I'll talk about in a minute, like IEEE P2800, that fundamentally say, in all cases, resources must remain online, must provide the support of reactive power and support of active power during frequency disturbances to remain online and not trip off during these disturbances. So Nick is going to talk more about the transient stability considerations, about what happens after we initially ride through an electrical disturbance and how the system recovers. But today, as long as the system conditions are known, how weak is the interconnection, what capabilities do we need to deploy with the inverter-based resources, what settings do we need to deploy for inverter-based resources in every application, it's not an issue to ride through the capabilities that we need to support the grid stability today. We had some lessons learned with solar some time ago. Earlier, there were a series of wildfires in California. There was a Blue Cut fire, there was Canyon 2 fire, and other events that caused electrical faults on the transmission grid. And some PV solar did not fully ride through. It did not trip offline. It still actually met the requirements to ride through according to NERC, in terms of the capability of NERC standards not to open a circuit breaker and completely trip offline. However, these resources momentarily ceased, i.e. they stopped injecting power for a short amount of time while that fault happened. And after the fault cleared, sometime later, they picked back up again. They woke up and they came back online. So here was a case where we learned that some of the early inverters that have been online for for quite some time, these are vintage controls that were integrated early on, that were trying to do the right thing relative to early versions of some IEEE standards, actually tripped or I should say, momentarily ceased their injection of current into the grid, and that made it challenging to balance the rest of the system. Since then, this has been fixed. So making sure that we're deploying the modern technology that does not momentarily cease output during these disturbances is critical, and keeping the balance of power injection, both real and reactive, as needed, and not quenching the active power injection during these events is also critical. Again, not a problem today with modern technology, but standards, practices, and capabilities of knowing what's going to happen during faults is a critical thing. And we need to make sure that that is maintained. Today, there's a new standard that has been developed. It's called IEEE P2800, and it just went through its final balloting process. And this standard really is similar to IEEE 1547 for distributed energy resources that specifies certain performance of inverter-based resources to support the grid. So it's a minimum set of requirements, suggested requirements around support of reactive power to provide reactive power to control voltage, providing fast frequency response from inverter-based resources, providing primary frequency response from inverter-based resources, communications capability also from inverter-based resources to support the grid as needed. Right now, it's a matter of the fact that this standard has been passed. It's a matter of adopting the standard in all of the jurisdictions and the regions in order to deploy the capability at a minimum to enable the capability and the features of inverter-based resources to support the grid. So as I said, this standard covers frequency response. It covers reactive power control, both in terms of reactive power injection and also for batteries, reactive power absorption and active power absorption during charging. So there's a bidirectional element now when we have batteries that are integrated in a hybrid mode with power plants or standalone to support grid needs. All of that is specified in the IEEE P2800 capability of the standard. And it's, again, a matter of taking those suggested minimum requirements and incorporating them into all of the regional interconnection requirements and national interconnection requirements going forward. A lot more will come from this. NERC and each one of the regional entities will go through a period of adoption, so more to come on that. But this is critically important to enable the capability of the inverter-based resources. So on fault ride-through, again, to summarize, we want all generators to remain online during system disturbances. It's not a problem as long as we have eyes wide open to know what the settings need to be in order to remain stable in all system operating conditions, strong and weak. Momentary cessation should not be part of this, should not be allowed. But today's technology, momentary cessation is not an issue. All modern capability of PV, solar, and wind does support the grid and during disturbances, and it needs to be coordinated in a way to support real and reactive power and do it stably and reliably. So I think with that, we're right up against time. I know I went through a little bit fast, but I think we can open it up for any clarifying questions or,
Sure.
And Debbie, what would you like to do with this?
Sure. Thanks so much, Jason. That was fantastic. And sorry about rushing you there at the beginning.
No, no worries. No worries.
There's a question from someone in the audience that you've said we have the technical capabilities for voltage support and reactive power, et cetera, from inverter-based resources, but we need to ensure that they are deployed and enabled. So they ask, to what degree are these technical capabilities currently being incorporated into technologies connecting to the grid? Are there places where they're more or less prevalent, and why?
Right. Very good question. Very good question. And so today in North America, closed loop voltage controlled and voltage support is a requirement from NERC and is deployed basically everywhere. So that capability is a non-issue. It's deployed everywhere. There was a FERC order some years ago that requires frequency support, primary frequency response from all resources on the grid that are bulk connected. So since that happened, the frequency support from all resources is required. And so that change really allowed all of the capability to be deployed on the grid. The new aspect of stability and services to do balancing and make sure that we have the capability to deploy new services like system damping, for example. And Nick is going to talk a little bit more about some of these new services. Those are not institutionalized everywhere yet. IEEE P2800 goes a long way to making recommendations on what is needed to deploy some of those capabilities. Fast frequency response for what happens during the initial decline of frequency in the first few seconds. That is not a requirement everywhere either. The P2800 standard does call that out to have a fast frequency response capability, but it's a matter of adopting that in the jurisdictions where it's needed. Some jurisdictions, maybe Julia will talk a little bit about this, utilize a combination of requirements in ERCOT, for example, nodal protocols, and market mechanisms or payments to be able to pay for or provide the service as needed. So that's more what I was talking about in terms of deployability. Some of these new capabilities need to be put in place and for fast frequency response, for stability and control, and have those deployed.
Jason, this is Nick. Can you guys hear me?
Yep. Yeah. Thanks, Nick.
Yeah, this is Nick. I'm going to speak next, but I wanted to add a little color commentary to Jason's answer on that question, and maybe it's a dark color, but I think it's important for this audience. Jason said this, but I want to say it again. We need to make the distinction between the requirement that the equipment have the capability to provide these services, voltage control and frequency response, and the actual use of those capabilities. Those are not synonymous.
Yeah, exactly.
FERC has ruled that that it is mandatory to have the capability. Many systems, and Julia's as is often the case, ERCOT's an example, uses those capabilities very effectively. For voltage control, on the dark side, we hear and see instances in which planning at different levels within ISOs, RTOs, and at the balancing authority and at the level in which they are not taking advantage of this capability. And at times, the failure to take advantage of that capability is resulting in the requirement for investment in other voltage support devices for the grid. And it is occasionally constraining the operation of the grid, for example, causing curtailment of wind and solar in favor of other conventional resources. So there's a problem there. The second nickel, which is a little brighter, but he said, this capability for wind and solar plants to provide reactive power and therefore regulate voltage when they aren't generating. Jason that slide made a point that there is very largely non-existent regulatory and market signals to encourage the use of that capability. Nevertheless, at the anecdotal level, we see something on the order of a third of all wind plants built in the US having that capability anyway. And the reason is that there's an economic incentive to reduce the cost of the grid reinforcements that accompany the connection of a new plant. So planning entities that have the wherewithal to work with the suppliers are saving the ratepayers money by getting these capabilities built into the plant. That's something for you to watch as regulators and policymakers. This is not uniform in the industry. Okay, sorry, that was my color commentary.
Okay, that very good color.
Yeah, thanks, Nick. So there's another question. Is flicker an issue while using inverters with DERs? How should we manage flicker that's seen by domestic customers?
So if the question is specifically with DER, no, fundamentally from an inverter-based resource point of view, no. The capability of the resource itself and the inverter itself today has adequate filtering and avoiding issues related to poor power quality coming from the inverter. But I think the question also has a second answer around what happens when you have a large amount of local variability coming from, let's say, solar on a distribution network that may cause a lot of fluctuation in active power and therefore cause a lot of fluctuation in voltage locally. That is more of an issue, and it has become a big issue of coordinating the voltage control on local feeders and local distribution areas. Fundamentally, that localized variability of solar, especially on partly cloudy days, can cause a lot of stress on the voltage regulation devices that are placed in the distribution network and can start to wear them out. Those are the coordination concerns, and IEEE 1547 has gone a long way to try to relieve some of those concerns by allowing voltage regulation where possible and necessary on distribution network connections. So it's getting better, but still something to watch out for to make sure that coordinated control in the distribution level for voltage regulation is done. Again, the capability in the devices for today's technology is largely there, but it's a matter of coordination and having it online and required and deployed in a way that supports the system.
Yeah, I'll just throw a little, this is Nick again, throw a little color commentary. So what Jason said, do make a distinction in your question. Flicker is largely an issue, in the distribution system, very close to the load. Voltage variation on the bulk power system, that example that Jason showed that was work that he and I did 15 years ago, that voltage regulation is perfect. That's a non-issue. The issue of flicker at, down at the loads, down on the distribution system, and between us kids, we're really talking about photovoltaics in the US. We have added capability, the industry has added capability in 1547, the one standard, and the new standard P2800, both move towards providing a lot more latitude to deal with those issues. It was a great question, and for you audience, you regulators and policy folks, it is really incumbent on you to ask and to make sure that your constituencies are taking advantage of the mandate that these capabilities be in the equipment and figuring out how to use them so that they aren't wasting money fixing problems that could be fixed with the addition, and that they aren't artificially limiting the deployment of PV in particular because of problems that we've solved. So the question is great. Make sure you push back. The world is getting better. Okay, enough color commentary again.
Okay.